Hey guys, welcome back. In this video, we are going to get familiar with tree data structure, few of its important types, terminologies, and everything about tree that we must know if we are willing to solve tree-related problems. Alright, so what is a tree? A tree is a non-linear data structure in which every node points to a number of different nodes. That's where they are different from linear data structure like linked lists, where every node points to a single next node in linear way. So you can say a tree is something like this. A topmost node is called root, which is pointing to these three nodes instead of pointing to just a single node. And these nodes further can point to other nodes. Basically, tree is a way of representing hierarchical data. For example, any classification where one has its subtypes and it can further have subtypes, or any hierarchy. For example, consider an organizational hierarchy of a company where John is CEO and under John, Venkat is CTO, Shiva is president, and then Venkat is managing three employees, Ron, Bob, Emma. Emma is further managing a team of two, and similarly, you can see here there's a team of two employees managed by Shiva, three employees managed by Shiva. So when we look at this tree upside down, then it will resemble this structure, where we're starting from the root and we're branching out in downward direction. So tree is used where we need to store data, which is naturally in hierarchical form, or if we want to store it in hierarchical form. Another example is Unix file system, where the first directory is always root. Let's get into details and understand the structure. So first is the topmost node, which is called the root node. Root node is the starting node of the tree which has no parents. For example, in this tree, the node 1 is the root node. It is having reference to these three nodes 2, 3 and 4, which are its child nodes. And the line through which parent and child are linked is called edge or link. Here edge is always one directional, unidirectional. Like we can move from top to bottom but not in reverse direction. Similarly, node 5 and 6 are the child nodes of node 2. And 2 is the parent of 5 and 6. And there are leaf nodes, which are the last nodes of the tree. Here 5, 10, 11, 8 and 9 are leaf nodes. Next term is depth. Depth of any node is the length of the path from the root to that node. Like the depth for node 5 is 1 to 2, 2 to 5, which is 2. So the depth of 5 is 2. The nodes 5, 6, 7, 8, 9 are on the same depth and are said to be on same level as well. Node 1 is on level 1. Node 2, 3 and 4 are on level 2. Node 5, 6, 7, 8, 9 are on level 3. So level is depth plus 1. Next term is height of a tree. The height of a tree is the number of levels leading to the leaf node. Like here, the height of this tree is 4. And the height of node 2 is 2. So that's all about the basic structure of a tree. Now, based on different structures and arrangement of nodes, trees are classified into various categories. The simplest and the most common kind is binary tree. Binary tree is the tree in which each node can have at most two children. So this is binary tree where each node is having either 1, 0 or 2 child. Similarly, there can be k-ary trees in which any node can have at most k child. For instance, if k is 3, each node can have at most 3 child nodes. Back to binary trees. Binary trees can further be classified into these parts: strict binary tree, fully binary tree, and complete binary tree. Strict binary tree where every node has exactly two or no children. Fully binary tree where each node has exactly two children and all leaf nodes are on same level. That's the perfect binary tree. Complete binary tree where all leaf nodes are at same height, which means if it is completely filled from left, then it cannot be filled from right, and vice versa. These terms would more make sense when we'll solve problems on trees. Now, there's another kind which is binary search tree, a very famous kind, which extends binary tree properties. Each node here can have up to two child nodes, where the value of all the left nodes should be less than, and the value of all the right child nodes should be greater than the parent's value. Now you'll say, what about the value equal to the parent's value? Then you can consider it either in left, either in right, or you can avoid having duplicate values. So let's take an example. If we have these data elements, now to put these items in tree, first 200 will be the root node, and then the next element, which is 250, which is greater than 200, so it will get added to the right. So now next comes 150, which is less than 200, so it will be added on the left side of the root. Now 210, which is greater than 200, so it will be added to the right side of the root, and then it is less than 250, so it will be on the left of 250. So this is binary search tree. Due to its property, binary search tree is the ideal data structure for search operations. Why? Because we can figure out at each node whether the node being searched is present in left or in right of the current node. Now let's get a quick look on various operations on trees. The basic operations it has is traversing the tree, searching for any element, inserting an element, and deleting an element. First, traversal of trees. Unlike other data structure, trees and graphs has more than one type of traversals, which are classified by the order in which nodes are visited, broadly into two types: breadth first search and depth first search. In breadth first search, traversal starts from the root node and then it visits all the nodes of the current depth first before moving to the next depth in the tree. So this is the given tree. In this tree, the traversal would be 1, 2, 3, 4, 5, 6, and 7. So there is a single type of breadth first algorithm, which is level order traversal. This was level order traversal, where we traverse all the nodes of the current level and then move to the next one. Next is depth first search. It starts with the root node and visit each node of one branch as deep as possible before traversing other branch in the same level. And then it traverses every branch in similar fashion. See here, first it covers the leftmost branch and then it goes to the next branch and then to the next and then to the last one. There are three types of this approach: in order, pre-order, and post-order. In order traversal, you go to the left subtree first and then to the root and then to the right subtree. So we start from the root node and we pick its subtree till we reach to the leaf. So we read the leaf and then we read its parent and then we go to right. And after reading the subtree, it goes to its parent, which is 2, reads it and then goes to the right. Then again to its parent, which is 1, reads it and go to the right. And now here at right, at 3, we are again having a left branch. So it goes till the depth of this branch. Reads the last item or the leaf node, goes to its parent. We're not having any right child, so again this will go to its parent, which is 3, and then we'll read the last node, which is the rightmost node. So this was in order traversal. Now let's talk about pre-order traversal. In pre-order, as the name suggests, first we read the node itself and then its left and then the right. So here we will first read the node itself, the root itself, and then we will go to the left. We'll read it. We will read the complete branch, and then in the same manner we will complete this branch and then we will go to the right. Now the last one is post-order traversal. Post-order, the node itself comes last. So we're going to read this root node in this tree at last. So first we're going to read the left. So we're going to start from 8 and then we will read 9, which is the right, and then the node itself, which is 4. And again, we have read this left subtree of this node 2. So we will now read the right, which is 5. And now we will read 2, which is the parent or the node itself. So we have read left of this root, which is having value 1. Now we will go to its right and we'll read this right subtree in the same manner. 10, then 6, and then 7, and then the node. And then finally, at the end, we will read this 1. So this was the post-order traversal. Now other operations. Let's first talk about insertion. If we are going to add a node in binary tree, then we will add it to a node which is having no child at all, or it is having a single child. Like here, if I want to add node 7 in this tree, I must add it to the right of 3. So it will check for its proper place. But if the tree is binary search tree, then we need to check for the perfect location. Here, if I want to add the 7 in this tree, in this binary search tree, then at each node I need to check if the 7 is smaller than or greater than the current node. If it is smaller than the current node, then we are going to keep going towards left. But if it is greater than the current node, then we have to go towards the right. Now the next operation, search operation. Searching for a node in any type of tree other than BST requires traversing to every node present in the tree. Whereas in binary search tree, while traversing, we check if the node for which we are searching is less than or greater than that node. And then we continue to traverse accordingly in left and right subtree. Now let's talk about deleting a node. Deleting a node is to first search the node and then removing that node. The purpose of explaining all these operations here is to make you familiar with trees more and to make you understand how exactly they work. And on the same context, Let's get an idea of complexities of these basic operations so that when we'll solve any problem based on tree, we'll exactly know what is happening behind the scenes and how much time and space it's gonna consume. So starting from the traversal, in any type of tree, it doesn't matter which way we are traversing the tree, for traversing all the nodes n, it's gonna take order of n running time. And the space complexity varies in BFS and DFS. Basically, it depends on the implementation. In breadth first search, what we do, we traverse all the nodes present on the same level and then we go to the next levels. Let's talk a bit about how this BFS is performed logically. See here, we don't have any link between the nodes on the same level. So from the first node, which is the node 2, we cannot come through its parent to this other node, node 3. As trees are unidirectional. So to perform this level order traversal or breadth first search, we can use queues. We can put the node that is going to be visited into the queue, and then when we visit it, we remove it from the queue, and at the time of removal, we add its child nodes in the queue. And you know that the child nodes of a node are on the same level. So now we have the nodes of the same level to be traversed after this. And this goes on each time we remove a node from the queue. At the end of one level, each time the queue gonna have all the nodes from the next level. In worst case, the queue can be of size n. Therefore, the space complexity will be order of n. This is the space complexity for this implementation where we use a queue to store the nodes. But there can be some other solutions too with different complexity. Now in DFS, in the iterative approach, we use stack. Stack stores all the ancestor nodes because while iterating, we need to go deeper till the last node, right? So it requires space of h. H is the height of the tree. For instance, if we traverse this tree in post order, where first we read left child, then right child, and then the node itself. So to first read the leftmost node, we continue to go to the left subtree and store all the nodes that come in the path. So when we are at 8, we will be having all the ancestor nodes of 8 in the stack. After 8, as it is not having anything further, so it gets popped out, 8 gets popped out, and then we go to the right node, which is 9. Store it in the stack. Now one by one, the nodes present on the stack gets visited and gets popped out of the stack. So it takes order of h space. Even if we use recursive approach, it will take order of h space on the call stack, as the max depth of recursion will also be equal to the depth or height of the tree. So for DFS, space complexity would be order of h. In recursive implementation, you can also term it order of d, where d stands for the depth of the tree. Alright, moving forward, next is the search operation. The time complexity will be order of n for binary or for any k-ary tree, as we need to go through each node. So if total nodes are n, the time complexity is order of n. And for binary search tree, the complexity will be order of log n. as on each level we would be eliminating half of the nodes. Consider this skewed binary search tree. Searching for node 7 will not take order of log n this time, as it won't be actually eliminating half of the tree at each step. So in this case, the worst case complexity would be order of h, where h is the height of the tree, and the space complexity will be constant. Now let's analyze complexity for insertion and deletion. For inserting any element, in worst case, we might need to traverse n nodes, so the time complexity will be order of n. And for BST, searching gonna take order of h running time, so the complexity will be order of height of the tree. And the space complexity will be constant. The same goes for deletion. Running time for BST will be order of h, and for all other tree types it will be order of n. And the space complexity is constant. The important thing to mention here is that how a balanced binary search tree can reduce running time from n to log n, which is way better. This introduces some advanced tree types like avial trees, red-black trees. In avial trees, the difference between the heights of left and right subtrees cannot be more than 1 for all nodes. If at any time they differ by more than 1, rebalancing is done to restore the property. Red-black trees. In red-black trees, each node stores an extra bit representing color, which is used to ensure that the tree remain approximately balanced during insertions and deletions. So these are a few of special type of binary search trees which are self-balancing, which means the new nodes get inserted in a way that overall tree balance remains intact. Every operation in such tree is going to take order of log n running time, which is great. So this was all about the overview of trees. I hope this explanation makes the basic tree concepts clear to you. However, it might seem too much at first if you're really new to trees, but as soon as you'll start solving problems on trees, you'll start getting everything. Here we also try to get an idea of complexities of important tree operations. Now it will be easier to get the complexity pretty quickly when we'll discuss problems and algorithms.